Okay, so this video will talk about the solution for assignment 6, if I remember correctly, which is about chapter 27, the circuits. So there are two questions. So let's begin. Okay, so this is the first one. So the ideal battery, this one and that one, this one and that one. We have two battery, E1 and E2. So this is E1, this is E2. And the resistance R1, R2, R3 are given. R1, R2, and R3. What is the current of R2? And what is the power dissipated by R3? So this is a very simple problem. So in this case, without loss of generality, we can simply assume maybe this one is the ground node, this one is the ground node, which means 0 volt. And actually, this is E1, this is E1, this is E2. And this is an unknown voltage. Let us call it V. Let's call it V. So we can apply KCL at this node, at this node, so that we can write it as like this. V minus E1 over R1 plus V over R3 plus V minus E2 over R2. So this is a very simple KCL applying at this node. So the first term refers to the current going from this node to here. And then the second term is the current going from this node to here. And then the third term is the current going from this node to here. So I've mentioned that you don't really need to think too much about what is the current of this path, that part, or that part. I usually assume all the current flowing outside, and then I just calculate the current of this path, and this path, and we add them together, then which is equal to 0. So it will be easier for you to consider the current going this way, this way, this way. All the three paths going out from this node, so that they add to be 0. If one or more of them are calculated to be negative, then which means that for that path the current is going inside rather than going outside. So in this case, V is a unknown, and all the other terms are known. E1, E2, R1, R2, R3 are unknown. So actually we can solve V like this, E1 over R1 plus E2 over R2. And then here, 1 over R1, 1 over R2, 1 over R3. So this one is really simple. And then we plug in all the number, 10 over 4 plus 18 over 6 over 1 over 4 plus 1 over 6 plus 1 over 2. So the answer is 6 volt for part not part A yet, because it is only the voltage. But actually, after we know the voltage, we can calculate any current we like to. So for part A, we like to calculate the current going through R2. So we may call it I2. So I2 is nothing but V minus E2 over R2. So V is 6 volt as we calculate, and E2 is 18, and R2 is R2 is 6 ohm. 6 ohm. So 6 minus 18 minus 12 over 6 minus 2A. Minus 2A. So minus 2A. So actually, if you write I going to the right side and then you answer minus 2A is okay. If you indicate your I2 is in this way, then I2 should be 2A. Should be 2A then. As long as it matches the direction, then it's all right. But you need to be careful about the direction of the current. Actually, current is not a vector, but it has a direction. So to pay a little bit attention about that. So for part B, it is simple either. We need to calculate the power dissipation by R3. So the power dissipation of R3, we may denote it as P3. Actually, for a resistance, there are 3 ways to calculate the power dissipation. One may be I square R or IV, or V square over R. It depends which one you feel that is more convenient to you, then you may use that. And actually, we observe R3 is here, so actually we already know V, what V is. So actually we can just simply use this one, because we already know V is 6 volts, R1 is 4 ohm, so which means that R3 is 2 ohm. It's 2 ohm rather than 4 ohm. It's 2 ohm, which means that the power dissipation of R3 should be 18 watts. 18 watts, like this. And this is the one for question 1. And be reminded that as long as I ask you the current of I2, you should you should mark your current on the figure. Otherwise, when you write 2A or minus 2A, then I don't really know you really care about the direction of the current. So mark it on the figure is important at this point. And for question 2, it may be more difficult, but actually it's not so difficult at all. So we see that in this figure there is a capacitor, a DC source, and a AC source. And these 2 sources are series with a resistor. And actually there is a capacitor, 2 ideal source, and 2 resistor, and a switch. This is a switch as shown. Initially, S has been open for a long time. Which means that as long as at t equals to 0, this part is at this steady state, is at the steady state, and at t equals to 0, the switch is closed, and assume C equals 2 mu f. E1 is a sinusoidal source, E2 is a DC source, blah blah blah. Or find Vc, the voltage across the capacitor for t is larger or equal to 0. So, so in this question, we need to first we should find the initial condition of Vc. Initial condition of Vc. In this case, we can withdraw the. So this is 6 volts, and the switch is open, so we don't really need to care about that. So this is C, and actually Vc is like this, and this is the R2. And at the steady state, we know that there is no current going in or going out of the capacitor, as long as this is a DC source. Okay, so there is no current. I should be equal to 0 at this point. So we know that as long as this is we can say this is a ground. So this is 6. This is 6 volts higher than, which means this node is 6 volts higher than this node, and there is no current in this loop. So this is 6 volts. This node should be minus 6 volts, which means that Vc 0 minus is 0 volt, minus 6 volt, and as long as at t equals to 0 plus, it should be equals to Vc 0 minus, which is minus 6 volt. And actually, you should be very careful about the current of the capacitor. IC0 minus is 0, as I mentioned. There shouldn't be any current going in or out of the capacitor for the DC steady state. So this one is 0. However, you should know that, of course, although this is not related to this question, but actually you should pay some attention to that, is that IC0 plus is not equals to 0. It's not equal to IC0 minus. This is very important. For capacitor, only the voltage is continuous, but the current is not continuous. For inductor, IL 0 plus should be equals to IL 0 minus, which means the current of an inductor is continuous, but the voltage of inductor is not necessarily equal to BL 0 minus, or at any moment that there are some switch, which means that the voltage of an inductor, the voltage across an inductor is not necessarily continuous. It may be continuous, but it is not necessarily continuous. But actually, especially at the moment for the switch is changes its state from open to close or from close to open, then and you should need to pay some attention for this case and this case. So when you try to write an ODE, try to avoid these two variable. Try to avoid this kind of variable. Then you can avoid some ways to make mistakes. Okay, let's come back, and we know that VC0 plus is minus 6 volt. So the next step is to consider the ODE describing the circuit. So at T is larger than or equal to 0, then the switch is closed, which means it is short connected. Then we can write it like this. Okay. So this is R2, this is E2, this is C, this is R1, and this is plus minus, and we call it E1, something like this. And we know that this is VC, this is VC. Okay, so at this point, we can write that as this node is grounded. This node is grounded. So this node voltage is VC. This node voltage is VC, and for this node it should be VC plus E1, EC plus E1, and for this node it should be VC plus E2 plus E2. So in this case, we may write the node equation or use the KCL for this one, for this question. So we calculate the current going in this path, and this path, and then we add them together to be 0. So for the left hand side current, we have VC plus E1 over R1. So we calculate the current going through this resistor, which is the current going through this path, because there is only one path. The current going through here to here to here to here should all be the same. And actually, we do not know the current for this source only by itself. We can only know the current through this source by the resistor using the Ohm's law. But this is the voltage source, which means that its impedance is 0, which means that no matter what its current is, the voltage is the same, which means that dV di for a voltage source is 0. So this is the impedance of an ideal voltage source. The resistance or impedance of the voltage source. So we cannot just ignore the resistor and then we know what is the current. The current is dependent on should depends on the other stuff. So depends on the other stuff. And the next part is the current going through the capacitor. And as we know that the current for the capacitor is C dVc dt. And next, the current for the right hand side path, which is similar to the left-hand side part. So we know that the current going through R2 should be VC plus E2 over R2 equals to 0. So we add all the three current together, which is equal to 0. So next, we can try to rearrange the term. So we leave VC and the first derivative of VC on the left hand side. So we have dVC dt for the first term, and then the next one is VC over R1. So we have R1 VC, and then the second one is VC over R2, so that we have VC over R2, and then we factor them out so that we have 1 over R1 plus 1 over R2 in parentheses, and then multiply by VC. So next, E1, E2 are the terms with unrelated to VC, so that we move it to the right hand side. So we have minus E1 over R1 on the right side, and minus E2 over R2 on the right hand side. And then we can just divide C on both sides to normalize the coefficient for the highest derivative terms, so that the ODE describing the circuit is something like this. VC. So and E1 over R1C minus E2 over R2C, something like this. So now we can substitute all the known variables into this equation. So we have C equals 2 mu, E1 is a sinusoidal function, E2 is 6, R1, R2. We all substitute it here, and then we can get the equation like this: dVC dt plus 625 VC equals minus 1,500 sine 200 pi t, 200 pi t, and then minus 750. So we have a constant coefficient, linear ODE of first order. This term is a first order derivative, which is the highest derivative term, so we call it the first order ODE. So actually we can just simply see that the characteristic polynomial is something like this. We change this one into the s, the first derivative term, to s, and then the original function to 1, so s plus 625 equals to 0. We just let the right hand side to be 0 first, stop this one. So we have s equals to minus 625, which means that VC, the homogeneous solution, VCC, is a exponential to minus 625 t. So next, we need to assume our particular solution for our VC. So this one is sinusoidal function, which means that we need to assume it to be b cosine with the same frequency, 200 pi t, plus, I do not use C because C is the capacitor, so I use D instead. But actually, you can take whatever you like. You can use MN, PQ, and blah blah blah. There's no problem. And then after finish the sinusoidal term, we need to assume the this term. This is a zero order polynomial, so that we add a zero order polynomial for the particular solution. So as long as we have this term, we assume this one and this one for that. And then we have a zero order polynomial. We also assume a zero order polynomial. And they are not conflict with this one, so this is going to be fine. And then we substitute Vp into here, so that take the first derivative, we will have 200 pi b minus psi 200 pi t. And then the second term plus 200 pi d cosine 200 pi t. And then the third term, e, the first derivative will be 0 because it's just a constant. And then plus 625 plus 625 multiplying this one. So it will be b cosine 200 pi t plus 625 d sine 200 pi t, and then also plus 625 e, and it will be equals to minus 1500 sine 200 pi t, and then minus 750. So actually the calculation is very simple, and then we just compare both sides. So first of all, this is the cosine, this is the cosine, and then on the right hand side there is no cosine, which means that this one added this one should be 0, which means that 625b plus 200 pi d should be 0. And then the next one, we consider the sine 200 pi t, sine 100 and 200 pi t, sine 102 pi, which means that minus 200 pi b plus 625 d should be equals to minus 1500. And then the next one, only remaining term is this one. So we have 625 e equals to minus 70 and 750. And this one is independent, so we have e equals to minus 1.2, minus 1.2. And then actually we need to solve this. And actually b will be equals to 1.2, and d will be equals to minus 1.19, minus 1.19. Okay, so in this case we will have VC is VCC plus VCP, and VCC is a exponential to minus 625t plus b. b is 1.2, And then you can check this line, and this line. So we have 1.2 cosine 200 pi t, and then the next term is d minus 1.19, and then sine 200 pi t, and then the last term plus e. E is minus 1.2, something like this. Finally, we need to determine what A is. And hopefully you still remember that we get VC0 plus is minus 6 volts. Ouch. We get VC0 plus is minus 6 volts. So we can substitute t equals to 0 for this expression. So VC0 plus is this one, A, this one plus 1.2, this one 0, minus 0, this one minus 1.2, so this would be equals to this should be equals to let me see. Minus 6. So in this case, A should be equals to 0. So this one and this one cancel. So A is minus 6. And thus, VC is minus 6 exponential to minus 625t plus 1.2 cosine 200 pi t minus 1.19 sine 200 pi t minus 1.2. The unit is volts, and that's it for question 2. So question 2 is a bit more difficult than the first one. And I think that's all the solution for the assignment this week. And if you have any more question, please let me know, and I try to reply to your answer. And see you next time.